Every second, the universe stretches farther, holding secrets about how everything began and the mysteries of existence. Our search for understanding takes us from the birth of galaxies and the mysteries of black holes to the possibility of life beyond Earth. Each discovery adds to our cosmic story, showing us what we know and the unknown still waiting to be explored. The beginning of the universe is a fascinating subject that has captured the curiosity of scientists and thinkers for centuries. The most widely accepted theory for the origin of the universe is the Big Bang Theory. According to this idea, around 13.8 billion years ago, the universe began as an infinitely small point, a singularity, which then rapidly expanded. This expansion was not an explosion in space, but rather an expansion of space itself. In those first moments, the temperature and density of the universe were extraordinarily high, creating a chaotic environment filled with energy. As the universe expanded, it cooled, allowing subatomic particles to form. These particles eventually combined to create simple atoms like hydrogen and helium. A few 100,000 years later, these gases began to clump together under the force of gravity, eventually leading to the formation of stars and galaxies. What if there's a lot more to the universe than we currently understand? Imagine we're only scratching the surface of a much bigger mystery. Think about the beginning of everything, the cosmos and all the stuff in it that's hard to detect, like dark matter and dark energy. Science helps us uncover bits of the truth, but there's still so much we don't know. Join us as we delve into the most mind-blowing mysteries in the universe. The story of the universe's beginning is a fascinating journey into the depths of time, where scientific theories spark imagination and curiosity. At the forefront of this exploration is the Big Bang Theory, which posits that the universe began as an incredibly hot and dense point approximately 14 billion years ago. In an event of unimaginable energy and expansion, it suddenly erupted, causing space itself to stretch. This expansion continues today, leading to the vast, intricate cosmos we observe. Before the Big Bang, traditional concept of time and space become murky. Some scientists propose the idea that the universe could have existed in a state of singularity, where the normal laws of physics break down. This mysterious beginning, where everything was confined to a tiny, infinitely dense point, raises important questions about what might have preceded it. Another prominent perspective is the multiverse theory. This theory suggests that our universe could be just one of many, existing alongside an infinite number of other universes, each with its own unique properties and perhaps even different physical laws. If this concept is correct, it reshapes our understanding of reality and suggests that the universe is far richer than we can see. Additionally, some scientists explore cyclical models, which propose that the universe undergoes a series of expansions and contractions, continuously recycling itself in an eternal loop. In such a scenario, what we perceive as a beginning could just be one phase in an endless cycle of birth, death, and rebirth. These theories interact and compete with each other, each offering answers to fundamental questions while also leaving many mysteries unsolved. As we look to the cosmos, we uncover not just our universe's origins, but also invite deeper inquiries into existence itself. Cosmic inflation presents a revolutionary perspective on the beginning of the universe, reshaping how we comprehend its origins. Traditionally, the Big Bang Theory proposed that the universe began as a hot, dense point that expanded over time. However, inflation suggests that during its earliest moments, the universe experienced a remarkable period of rapid expansion, much faster than the speed of light. Imagine a balloon that is blown up in an instant. It transformed from a tiny speck into a vast expanse. This swift expansion solves several puzzles associated with the early universe. Without inflation, scientists struggle to explain why different regions of the cosmos appear so uniform and similar despite being separated by vast distances. Inflation theorized that once the universe inflated, these regions were once in close proximity, allowing them to equalize in temperature and density before drifting apart. Additionally, inflation provides insight into the large-scale structures we observe today, such as galaxies and clusters. The tiny fluctuations in density caused by quantum effects during the inflationary epoch acted like seeds, growing over time into the vast cosmic web we see now. This concept of fluctuations intertwines with the idea that the universe's structure emerged from randomness, highlighting a deeper connection between the minute and the cosmic. While cosmic inflation refines our understanding, it also introduces complexity. It suggests that many universes could exist, each with different properties, a concept known as a multiverse. This idea challenges the singularity of our universe and raises philosophical questions about what constitutes reality and our place within it. Cosmic inflation not only provides answers to long-standing questions, but also opens a door to new inquiries, transforming how we think about the universe's beginning and the vast, mysterious fabric of existence itself. The Big Bang Theory marks the beginning of our universe, a moment when everything we know emerged from an incredibly hot, dense state. Despite its established prominence in cosmology, significant mysteries surround this monumental event and its early moments. To start, the exact condition of the universe at the very moment of the Big Bang remains largely enigmatic. Scientists believe that the universe began expanding rapidly, but the precise mechanics of how everything evolved during those first instances, when temperature and density were unimaginably high, are still poorly understood. This period encompasses what is known as cosmic inflation, a theory suggesting a swift expansion that occurred mere moments after the initial event. However, the details of this process and what may have triggered it remain hypothetical, leaving many questions unanswered. Another profound mystery lies within the formation of the fundamental forces and particles. In those early moments, the universe was a chaotic soup of energy, and as it cooled, particles began to form, transitioning from energy to matter. The unification of the forces, gravity, electromagnetism, and the strong and weak nuclear forces, during this time is a topic of intense study. We lack a complete understanding of how these forces developed their distinct characteristics and roles in shaping the universe we inhabit now. Moreover, the period following the Big Bang, known as the radiation era, is somewhat obscured in our current theories. The rapid expansion led to cooling, which allowed protons and neutrons to combine into light elements like hydrogen and helium. However, the exact processes that govern this nucleosynthesis are still being explored. The abundance of these elements hints at a finely tuned balance of conditions present during that era, but our grasp of this phenomenon is still developing. Dark matter and dark energy introduce additional layers of complexity to the narrative of the universe's early history. We know that most of the universe is comprised of these elusive substances, which do not interact with light and thus remain invisible. Their presence is inferred from gravitational effects, but their roles and origins remain a puzzle that haunts cosmologists. Finally, the cosmic microwave background radiation, an afterglow of the Big Bang, offers a glimpse into the universe's infancy. This faint radiation is a relic from when the universe became transparent to light. Studying it has revealed crucial information, yet it continues to unveil mysteries about the initial conditions of the cosmos and the uniformity seen throughout the universe today. In conclusion, while the Big Bang Theory provides a fascinating framework for understanding the universe's origins, it is far from complete. Each aspect, from cosmic inflation, the formation of fundamental forces, to the nature of dark matter and the remnants of the cosmic microwave background, poses intriguing questions that challenge our knowledge and inspire ongoing research in the field of cosmology. The universe, despite its chaotic beginnings, exhibits a remarkable uniformity that can leave many pondering how such order emerged from what seemed like a tumultuous explosion. Scientists explain this phenomenon through a theory known as cosmic inflation. Imagine the universe as a balloon that, in its infancy, underwent a rapid expansion. In this early stage, the universe expanded faster than the speed of light, smoothing out irregularities and making the distribution of matter and energy more uniform. This swift expansion meant that any initial variations in temperature and density caused by quantum fluctuations in the very early moments were stretched and flattened across vast distances. As the universe continued to expand, these tiny imperfections remained, but they became statistical fluctuations rather than dramatic differences. Furthermore, as matter began to clump together under the influence of gravity, it organized into the structures we observe today, like galaxies and clusters of galaxies. Over billions of years, while local environments may appear chaotic, on a grand scale, the universe shows patterns and structures that reflect this initial state of smoothness. Also, the laws of physics, particularly thermodynamics and gravity, play essential roles in establishing this uniformity. Gravity tends to pull matter together, while thermodynamics dictates how energy disperses. Together, they foster a balance that supports the orderly distribution of galaxies across the cosmos. The universe's uniformity is a glimpse into its peaceful aftermath, smoothed by rapid expansion and shaped by fundamental forces, turning chaos into the harmonious cosmos we observe today. Dark matter is one of the universe's greatest mysteries. It is a substance that does not emit, absorb, or reflect light, making it completely invisible to our telescopes and sensors. Despite its elusive nature, scientists have strong evidence suggesting that dark matter constitutes a significant portion of the universe's total matter. Imagine the universe as a massive cosmic tapestry, where the visible stars and galaxies are like highlights in a broader fabric that remains unseen. Scientists have attempted to detect dark matter through various methods, including underground experiments designed to catch rare interactions with ordinary matter and observations of cosmic phenomena. Yet, it remains stubbornly out of reach, largely because the known particles that we typically study do not account for it. This uncertainty fuels ongoing research in the horizon, where scientists explore candidates for dark matter particles, which may only interact through gravity. Each breakthrough brings new insights, but the question of its composition and exact nature continues to elude our understanding, keeping dark matter as one of the most fascinating enigmas in modern astrophysics. Dark matter plays a crucial role in shaping the universe, particularly in the formation and structure of galaxies. Imagine a traditional scale. The visible matter in galaxies, which include stars, gas, and dust, is only a fraction of what actually exists. Dark matter, which does not emit light or energy, acts like an invisible frame, holding everything together. As galaxies form, they draw in surrounding mass through gravitational attraction. The presence of dark matter creates a gravitational field that exercises a strong influence on visible matter, pulling it toward the centers of galaxies. This is essential because visible matter alone would not have enough gravitational pull to bind galaxies effectively, leading them to be less stable and prone to disintegration or dispersal. The distribution of dark matter within and around galaxies is often shaped like a halo, extending far beyond the visible parts. This dark matter halo influences how galaxies rotate. To visualize this, think of a carousel. While the outer horses should be moving slowly because they are farther from the center, they actually spin at similar speeds to those near the center. This unexpected behavior implies that there is much more mass present than what we can see, and that mass must be due to dark matter. Moreover, dark matter plays a pivotal role in galaxy collisions and interactions. When two galaxies meet, the gravitational tug-of-war is influenced significantly by the surrounding dark matter. Its overwhelming presence helps channel and guide the merger process, impacting the resultant structure and evolution of the new galaxy that emerges. Without dark matter, the universe would look entirely different. It provides a structural backbone that allows galaxies to form, grow, and evolve, acting as a silent but powerful force that shapes the very fabric of cosmic architecture. Dark energy is often referred to as one of the greatest mysteries in modern cosmology due to its elusive nature and the profound implications it has on our understanding of the universe. Imagine our universe as a vast, ever-expanding landscape. While we can see galaxies moving away from us, indicating that space itself is stretching, the reason for this acceleration is tied to dark energy. This enigmatic force is thought to make up a significant portion of the universe's total energy content, much more than both normal matter and dark matter combined. However, scientists have been unable to directly observe dark energy or comprehend its fundamental properties. It behaves in a way that is counterintuitive to our understanding of gravity and matter. Instead of pulling objects together, dark energy seems to push them apart, driving the accelerated rate of expansion. One of the biggest challenges is that, unlike ordinary matter or radiation, dark energy does not interact through any of the known forces. That's why it remains so undetectable. Its effects are felt on cosmic scales, over vast distances and immense time scales, which makes experiments and observations incredibly complex. Theories attempting to explain dark energy range from the possibility that it is a property of space itself to ideas involving modifications to our understanding of gravity. Each theory offers a different glimpse into the nature of the universe, but none have yet provided a definitive answer. Consequently, grappling with dark energy not only challenges the foundations of physics, but also invites questions about the ultimate fate of our universe. Will it continue to expand forever, or is there a limit to this growth? The search for answers continues, making dark energy a profound and captivating subject of cosmological inquiry. Detecting and studying dark matter, that mysterious substance thought to make up a significant portion of the universe, is one of the biggest challenges in modern astrophysics. Scientists believe dark matter does not emit light and can only be observed through its gravitational effects on visible matter. To uncover its secrets, researchers are employing several innovative approaches. One way scientists look for dark matter is through large underground detectors. These facilities are designed to catch rare interactions between dark matter particles and ordinary matter. Imagine an incredibly sensitive watch that records the faintest of movements. These detectors use materials that can produce small flashes of light or tiny electrical signals when a dark matter particle collides with an atomic nucleus. The hope is that, although these interactions are extremely rare, they can eventually be captured and understood. Another method involves observing galaxies and galaxy clusters. The influence of dark matter becomes evident in the way galaxies move. Scientists have attempted to detect dark matter through various methods, including underground experiments designed to catch rare interactions with ordinary matter and observations of cosmic phenomena. Yet, it remains stubbornly out of reach, largely because the known particles that we typically study do not account for it. This uncertainty fuels ongoing research in the horizon, where scientists explore candidates for dark matter particles, which may only interact through gravity. Each breakthrough brings new insights, but the question of its composition and exact nature continues to elude our understanding, keeping dark matter as one of the most fascinating enigmas in modern astrophysics. Dark matter plays a crucial role in shaping the universe, particularly in the formation and structure of galaxies. Imagine traditional scale. The visible matter in galaxies, which includes stars, gas, and dust, is only a fraction of what actually exists. Dark matter, which does not emit light or energy, acts like an invisible frame holding everything together. As galaxies form, they draw in surrounding mass through gravitational attraction. The presence of dark matter creates a gravitational field that exercises a strong influence on visible matter, pulling it toward the centers of galaxies. This is essential because visible matter alone would not have enough gravitational pull to bind galaxies effectively, leading them to be less stable and prone to disintegration or dispersal. The distribution of dark matter within and around galaxies is often shaped like a halo, extending far beyond the visible parts. This dark matter halo influences how galaxies rotate. To visualize this, think of a carousel. While the outer horses should be moving slowly because they are farther from the center, they actually spin at similar speeds to those near the center. This unexpected behavior implies that there is much more mass present than what we can see, and that mass must be due to dark matter. Moreover, dark matter plays a pivotal role in galaxy collisions and interactions. When two galaxies meet, the gravitational tug-of-war is influenced significantly by the surrounding dark matter. Its overwhelming presence helps channel and guide the merger process, impacting the resultant structure and evolution of the new galaxy that emerges. Without dark matter, the universe would look entirely different. It provides a structural backbone that allows galaxies to form, grow, and evolve, acting as a silent but powerful force that shapes the very fabric of cosmic architecture. Dark energy is often referred to as one of the greatest mysteries in modern cosmology due to its elusive nature and the profound implications it has on our understanding of the universe. Imagine our universe as a vast, ever-expanding landscape. While we can see galaxies moving away from us, indicating that space itself is stretching, the reason for this acceleration is tied to dark energy. This enigmatic force is thought to make up a significant portion of the universe's total energy content, much more than both normal matter and dark matter combined. However, scientists have been unable to directly observe dark energy or comprehend its fundamental properties. It behaves in a way that is counterintuitive to our understanding of gravity and matter. Instead of pulling objects together, dark energy seems to push them apart, driving the accelerated rate of expansion. One of the biggest challenges is that, unlike ordinary matter or radiation, dark energy does not interact with any of the known forces. That's why it remains so undetectable. Its effects are felt on cosmic scales, over vast distances and immense time scales, which makes experiments and observations incredibly complex. Theories attempting to explain dark energy range from the possibility that it is a property of space itself to ideas involving modifications to our understanding of gravity. Each theory offers a different glimpse into the nature of the universe, but none have yet provided a definitive answer. Consequently, grappling with dark energy not only challenges the foundations of physics, but also invites questions about the ultimate fate of our universe. Will it continue to expand forever, or is there a limit to this growth? The search for answers continues, making dark energy a profound and captivating subject of cosmological inquiry. Detecting and studying dark matter, that mysterious substance thought to make up a significant portion of the universe, is one of the biggest challenges in modern astrophysics. Scientists believe dark matter does not emit light and can only be observed through its gravitational effects on visible matter. To uncover its secrets, researchers are employing several innovative approaches. One way scientists look for dark matter is through large underground detectors. These facilities are designed to catch rare interactions between dark matter particles and ordinary matter. Imagine an incredibly sensitive watch that records the faintest of movements. These detectors use materials that can produce small flashes of light or tiny electrical signals when a dark matter particle collides with an atomic nucleus. The hope is that, although these interactions are extremely rare, they can eventually be captured and understood. Another method involves observing galaxies and galaxy clusters. The influence of dark matter becomes evident in the way galaxies move. If we consider a group of stars moving around a galaxy, their speeds reveal that there must be more mass present than we can account for with visible matter alone. By studying the motion of these celestial bodies, scientists can infer the distribution of dark matter within those galaxies. Furthermore, scientists are also exploring the possibility of creating dark matter particles in high-energy particle collisions. Large particle accelerators, like those at CERN, smash particles together at incredible speeds, allowing researchers to probe the fundamental building blocks of matter. In this controlled environment, some hope to produce dark matter particles, providing direct evidence of its existence. Finally, astrophysicists observe the cosmic microwave background radiation, an ancient afterglow from the Big Bang. By examining fluctuations in this radiation, scientists can gain insights into how dark matter influenced the formation of structures in the early universe. This method helps paint a broader picture of the cosmos and how dark matter fits into its grand design. As researchers strive to unravel the mysteries of dark matter, these various methods contribute to a multifaceted approach in what promises to be a groundbreaking quest in our understanding of the universe. Each discovery brings scientists one step closer to revealing the elusive nature of this invisible substance that shapes our reality. Dark energy represents one of the most intriguing mysteries in modern astrophysics. Traditionally, gravity, as described by Newton and later refined by Einstein, is a force that attracts objects toward one another. In the framework of our universe, it was expected that this attractive force would result in a slowing down of the expansion of the cosmos over time due to gravitational pull. However, observations suggest otherwise. Data indicates that the universe is not only expanding but is accelerating in that process. This unexpected behavior introduces the concept of dark energy, a force that seems to counteract the effects of gravity on a grand scale. Imagine blowing up a balloon. As you blow air into it, the balloon expands, reflecting how the universe is stretching out. If gravity was solely at play, we might expect the air inside to pull the sides inward, slowing the expansion. Instead, dark energy acts like an unseen hand, pushing the balloon outward even faster. The challenge lies in understanding what dark energy actually is. It makes up a significant portion of the universe's total energy content, yet it interacts with matter in a way that is still unclear. Einstein introduced the cosmological constant a century ago as a way to explain a static universe, but discarded it once it was revealed the universe is expanding. Now, it appears that maintaining a cosmological constant might be closer to the truth. This constant represents a steady energy density filling space, pushing everything apart in a uniform manner. As scientists delve deeper into this conundrum, they confront profound implications for the nature of gravity itself and the fundamental structure of the universe. The existence of dark energy suggests that our understanding of gravity and its role in cosmic evolution is not complete. It challenges us to rethink how forces interact on both macroscopic and microscopic levels, pushing the frontier of physics into areas of theoretical speculation, particularly regarding the very fabric of space and time. The quest to unravel dark energy could very well lead to a new chapter in our grasp of the cosmos. According to some models, the inside of a black hole could be a region of warped space-time where time behaves differently than in our familiar universe. Some suggest that traveling through a black hole might even lead to other dimensions or parallel universes, opening the door to possibilities that were once purely science fiction. Moreover, researchers are exploring the hint provided by gravitational waves, ripples in space-time created by massive events such as black hole mergers. These observations may help reveal more about the fundamental structure and behaviors inside a black hole, shedding light on their enigmatic nature. As our understanding evolves, so too do our theories, weaving complex tapestry of notions that intertwine gravity, quantum mechanics, and the very fabric of reality. The ultimate truth may still be beyond our grasp, but every new discovery brings us a step closer to understanding the true nature of black holes and their intriguing secrets. Black holes represent one of the universe's most intriguing mysteries, particularly in how they intersect with the principles of quantum mechanics. The foundation of this connection lies in the nature of black holes themselves. When a star collapses under its own gravity, it forms a black hole, creating a region of space where gravity is so intense that not even light can escape. This seems to lead to a contradiction when considering what happens to information, which is critical in quantum mechanics. The information paradox arises from the idea that anything falling into a black hole appears to be lost forever. According to quantum mechanics, however, information cannot simply vanish. It must be conserved. This contradiction creates a persistent puzzle in physics. If black holes can swallow up information, where does that information go, and how does it reconcile with the laws of quantum theory? Scientists have proposed various theories to unravel this paradox. One intriguing concept is the idea of black hole evaporation, introduced by the physicist Stephen Hawking. He theorized that black holes can emit radiation, now known as Hawking radiation, causing them to gradually lose mass and eventually disappear. If this process occurs, it poses a question: does the information get lost forever when the black hole evaporates, or is it somehow preserved and released as a black hole shrinks? Several physicists propose that the information might be encoded at the black hole's event horizon, the boundary beyond which nothing can escape. This idea suggests that everything that falls into a black hole leaves a sort of imprint at the edge, potentially allowing for the recovery of information over time. These theories delve deeply into the fabric of space-time, suggesting that our understanding of gravity, time, and information is limited, and that further investigations could change how we comprehend the universe. As research in both astrophysics and quantum mechanics continues, the interaction between black holes and the principles of quantum theory remains a dynamic field of study, holding the potential to inform us about the fundamental structure of reality itself. Black holes play a crucial role in the evolution of galaxies, acting as both engines of growth and sources of destruction within galactic environments. At the heart of many galaxies lies a supermassive black hole, which can be millions to billions of times heavier than our Sun. These black holes influence their galaxies in several significant ways. First, as matter spirals inward toward a black hole, it forms an accretion disk, heating up and radiating energy. This process can release immense amounts of energy, impacting star formation in the surrounding regions. In fact, the energy output from these disks can either stimulate the creation of new stars or, conversely, suppress star formation by blowing away gas and dust that would otherwise coalesce into stars. This balancing act between star formation and energy output is vital in determining the structure and future of a galaxy. Additionally, the gravitational pull of supermassive black holes affect the orbits of stars and gas in their vicinity. This intense gravitational environment can lead to complex interactions, including the merging of smaller galaxies into larger ones. As galaxies collide, their central black holes may come together, eventually forming even larger black holes. The merging of galaxies, complemented by this process, plays a significant role in the growth of galaxies over cosmic time. Moreover, black holes influence galactic dynamics through powerful jets. When black holes consume material, they can eject it at near-light speeds in the form of jets that shoot out into space. These jets can impact surrounding gas clouds, further influencing star formation and the overall evolution of the galaxy's structure and star population. Black holes are not merely dormant cosmic monsters. They are active participants in the cosmic ballet of galactic evolution, shaping the interactions and growth of galaxies, impacting star formation, and driving the complex dynamics of our universe. Neutron stars are truly remarkable because they represent one of the universe's most extreme states of matter. Formed when massive stars exhaust their nuclear fuel and collapse under their own gravity, these celestial objects are incredibly dense. Picture compressing the mass of a sun into a sphere roughly the size of a city. This extraordinary density means that a single teaspoon of neutron star material would weigh as much as an entire mountain on Earth. What sets neutron stars apart even further is their composition. They are primarily made up of neutrons, which are subatomic particles that, alongside protons, form the nucleus of atoms. In a neutron star, The gravitational forces are so intense that electrons combine with protons to form neutrons, creating a unique state of matter known as neutronium. This extremely dense material gives neutron stars their incredible gravitational pull. Additionally, many neutron stars are observed as pulsars, which are rapidly spinning stars that emit beams of radiation as they rotate. These beams sweep across space like lighthouse beacons. The remarkable speed of their rotation can reach hundreds of times per second, generating immense electromagnetic fields. This pulsating behavior allows astronomers to study their properties in great detail, offering insights into fundamental physics and the fabric of the universe. Neutron stars also serve as natural laboratories for studying the interactions of matter under extreme conditions. Their existence challenges our understanding of physics, particularly in fields like quantum mechanics and general relativity. Thus, neutron stars not only showcase the incredible diversity of celestial bodies, but also push the boundaries of our knowledge about the universe itself. Magnetars, a type of neutron star, possess incredibly strong magnetic fields, about 1,000 times stronger than those of ordinary neutron stars. To understand these cosmic oddities, scientists employ a combination of observational techniques and theoretical models. Astronomers often look to the electromagnetic spectrum, especially in the X-ray and gamma-ray ranges, to study magnetars. These regions of light can penetrate dense materials and provide insights into the magnetar's energetic emissions. By observing bursts of radiation that magnetars emit, scientists can infer details about their magnetic fields. For instance, the energy and frequency of these emissions offer clues about the strength of the magnetic field and its effects on the surrounding matter. Additionally, scientists utilize telescopes equipped with advanced detectors to capture these fleeting bursts. Telescopes on Earth and in space, combined with powerful observational techniques, allow researchers to track these events in real time. Different observations are cross-referenced to build a comprehensive understanding of a magnetar's magnetic activity and its effects on the environment around it. The magnetic fields also impact how these stars spin. By studying the rotation rate and any changes in it, researchers gain further insights into the internal structure of the magnetar. Through a combination of direct observation and mathematical modeling, scientists can piece together the mysteries of these extraordinary objects. Even without being able to travel to them directly, by integrating data from multiple sources and refining their theoretical frameworks, scientists continue to unravel profound effects that magnetars have on their surroundings and the fundamental physics at play in the universe. The very fabric of space-time, each collision serves as a cosmic laboratory that contributes to our knowledge of extreme physics, helping to piece together the landscape of the universe and our origins within it. The combination of gravitational wave data and light observed from COVID now helps reveal the mysteries of how the universe functions on a grand scale. As such, these discoveries are only the beginning, promising vast insights into the universe's most powerful and enigmatic processes. The idea of extra dimensions beyond our perceivable universe has captured the imagination of scientists and laypeople alike. One of the most prominent concepts arises from string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. These strings can oscillate in multiple ways, but in order for the full range of their behavior to exist, additional dimensions beyond familiar 3 dimensions of space and 1 dimension of time are necessary. The theory typically proposes that there are 6 or 7 extra dimensions curled up and hidden from our direct observation, making them incredibly challenging to detect. Another intriguing framework is that of brain-world cosmology, which stems from string theory as well. In this view, our observable universe could be likened to a 3-dimensional surface, or brain, floating within a higher dimensional space. Events occurring in these additional dimensions might influence the physical laws and phenomena we experience, even if we cannot directly observe them. Additionally, some theories in theoretical physics, like quantum gravity models, explore the implications of more than 4 dimensions by examining how gravity might behave differently when considered in a higher dimensional context. These models seek to reconcile the seemingly separate realms of quantum mechanics and general relativity, hinting that our universe may be part of a more complex structure than we can currently perceive. Finally, ideas such as multidimensional landscapes in cosmological theory suggest that our universe is just one of many possible configurations existing within a higher dimensional space, akin to a bubble among countless others. Each of these bubbles could have distinct physical laws and constants, further broadening the scope of what we might view as our reality. These theories push the boundaries of our understanding, proposing that the universe may be far more intricate than our everyday experiences suggest, encouraging scientists to explore the nature of existence beyond the limits of current perception. The concept of extra dimensions suggests that there are more spatial dimensions beyond the three we experience daily. Traditionally, we understand space as having length, width, and height, but theories in physics, notably string theory, propose the existence of additional dimensions that could be compacted or hidden from our view. This idea fundamentally alters our understanding of the universe and the laws governing it. Picture the familiar three-dimensional world. Now, imagine that there are additional dimensions curled tightly, so small that they escape detection at our scale. These extra dimensions can influence the fundamental forces and particles we observe. For instance, they can provide new pathways for gravity to strengthen or weaken, potentially explaining why gravity seems so weak compared to other forces like electromagnetism. In a universe with extra dimensions, gravity could disperse into these dimensions, making it less potent in our familiar three-dimensional space. Moreover, the presence of extra dimensions could lead to new particles and interactions, modifying the standard model of particle physics. Such changes might help us understand phenomena like dark matter or dark energy, which remain elusive in current theories. When particles are allowed to move in additional dimensions, their behaviors could shift dramatically, offering explanations for things we cannot yet fully explain. Extra dimensions might also provide insights into the early universe, particularly during events like the Big Bang. The conditions of that time could have triggered interactions that played out differently based on how many dimensions were involved. In this sense, extra dimensions might not only affect current laws, but could also reshape our understanding of the universe's history and its ultimate fate. By exploring these hidden dimensions, we venture into uncharted territories of physics, where the established rules of reality bend and twist, opening possibilities for new physics that could one day rewrite our definition of the cosmos. Scientists are venturing into the mysterious territory of extra dimensions, guided by theories that suggest our universe might have more spatial dimensions than the three we experience daily. One primary approach involved particle colliders like the Large Hadron Collider. Here, protons are accelerated to nearly the speed of light and smashed together. When they collide, these experiments unleash vast amounts of energy, which can, in theory, create tiny black holes or other particles that reveal the existence of extra dimensions. If these phenomena appear in the data collected, it could be a groundbreaking confirmation of higher dimensions. Another avenue of exploration involves gravitational wave detection. When two massive objects, such as black holes, collide, they produce ripples in space-time. By studying these waves, scientists hope to uncover anomalies that suggest the influence of extra dimensions on gravity and how it behaves. The existence of additional dimensions could alter the characteristics of these waves, providing crucial hints about their presence. Additionally, researchers are investigating certain types of cosmic rays and their interactions in the atmosphere. When high-energy particles from space collide with atoms in the Earth's atmosphere, they can produce showers of secondary particles. Analyzing these interactions might provide indirect evidence for extra dimensions if the results consistently deviate from expected patterns. All of these experiments share one critical goal: to provide a deeper understanding of the fundamental fabric of the universe. By identifying signs of extra dimensions, scientists could reshape our perception of reality, bridging gaps between known physics and the unknown realms that lie beyond our familiar three-dimensional world. Extra dimensions play a pivotal role in string theory, which is a leading framework attempting to unify our understanding of fundamental forces and particles. To grasp their significance, envision our familiar three-dimensional world, where we can move left, right, forward, backward, up, and down. However, string theory proposes that the universe might have more dimensions, usually posited as additional hidden dimensions are compactified, meaning they are curled up so small we can't perceive them in everyday life. These extra dimensions are essential for several reasons. First, they provide the necessary framework for strings, which are the fundamental building blocks in string theory. In this view, particles are not point-like objects, but rather tiny vibrating strings. The different vibrations of these strings correspond to different particle types, similar to how the strings on a musical instrument produce various notes. The properties of these particles, including mass and charge, are influenced by how these strings interact with the extra dimensions. Moreover, extra dimensions help reconcile gravity with the other fundamental forces. In our four-dimensional perspective, 3 dimensions of space and 1 of time, gravity behaves differently compared to forces like electromagnetism. By incorporating additional dimensions, string theory offers a more comprehensive picture where gravity can be described alongside other forces, potentially addressing phenomena that current models cannot explain, such as the behavior of black holes or the conditions of the very early universe. Additionally, hidden dimensions may provide clues about why our universe appears fine-tuned and why certain constants of nature have the values they do. These extra dimensions enrich the fabric of string theory, giving it the flexibility to model the complexities of our universe, consequently paving the way for a deeper understanding of the cosmos. The idea of extra dimensions opens up a fascinating new perspective on the structure of the universe. Traditionally, we experience a world in 3 spatial dimensions: length, width, and height, plus time. However, theory suggests that beyond these familiar dimensions, there could be additional ones intricately woven into the fabric of reality. Imagine our 3-dimensional world as a sheet of paper, flat and straightforward. If extra dimensions exist, they might be like folds or wrinkles on that paper, hidden from our direct view yet influencing everything we see. These extra dimensions could be compact and curled up so small that they remain unnoticed in our daily lives, while they might act as pathways connecting different points in our universe.